In this second video, we will cover the factors affecting the lattice energy. We will analyze now the two main factors that affect the value of the lattice energy. Those are size and charge of ions. These are going to be influencing the charge density. The charge density can be defined as the ratio between the charge of the ion and the volume of the ion, metallic or non-metallic. The size and the charge of the ions will affect the charge density, so the attraction between those ions in the lattice will make a different force, and the force to separate those ions will be different. We will analyze two different situations, same charge and similar size. With the same charge, if the size of the ion increases, the lattice energy will decrease because the ions are going to be farther apart. For the similar size, the one with more charge will increase the attraction, so the lattice energy will increase. So the key here is the charge density, and we will analyze both situations separately. In the first case, we are going to compare ions with the same charges and different sizes. For example, lithium, sodium, and potassium ion have the same charge, but they have different sizes. The same happens with the negative one, fluoride, chloride, bromide, or iodide. And we will analyze these two situations. So if we have two ions with the same charge, the bigger the size, the smaller the charge density, of course, and the forces of attraction between the ions will decrease too. So the lattice enthalpy will be less exothermic. You are going to be asked to compare two different situations. Like the first situation is going to be ions that are attached to the same positive charge ion, for example, sodium fluoride and lithium fluoride. Comparing sodium and lithium fluoride, both cations have the same charge, which is +1. You can see that in the chart here on the right. But lithium is smaller, so the attraction between the fluoride ions are going to be bigger, and it's going to have more charge density. So the lattice energy will be more exothermic for lithium fluoride than those of sodium fluoride. In case number 2, we are going to compare ions with different charge, but similar lattice arrangement and similar size. For example, magnesium oxide and lithium fluoride have very similar structure. So the ratios between those are going to be different because of the charges. We have magnesium that has an ionic radium of 72 picometers, and lithium one of 76 picometers. So they have similar sizes. So in the oxygen, actually the oxide, the radius is 140 picometers, and fluoride has 133 picometers, so they have similar sizes as well. The arrangement is very similar, as we said in the graph on the right. So the big difference is going to be the charge of the ions. The lattice energy for a compound with more charges would increase the force of attraction. You can think about two magnets that have double the force of attraction because they are more charged. The bigger the attraction is going to be more difficult to separate. The same thing happens here, or very similar. The actual values for the lithium fluoride is 1049 kilojoules per mole. If you look in the internet or different books, you may have a slight different value, but it's around 1000 and something. Negative, of course, because the lattice energy is the energy released when they form the lattice. And the magnesium oxide is going to have 3923. That means that the magnesium oxide is going to be much more difficult to separate. The lattice energy, of course, is going to be bigger. So for compounds with similar arrangement and different charge, the more exothermic is going to be the more lattice energy, or the bigger the charge, the more exothermic will be. Let's summarize the two situations that we have in here before that we analyzed before. In the first one, we have different sizes And similar charges, that is, the bigger the ions, the less attraction will have, so it's going to have or require more energy to separate them. And in the case of the same size or similar size, like the ones at the top here, the one with more charge is going to have a bigger lattice energy. On the graph that you see on the right, you're going to see that the magnesium polarizes better the carbonate ion than the calcium does. And that is because the magnesium has more density charge than the calcium, because it's smaller and has the same charge. So ion polarization is going to be that property of polarizing the cloud of electrons on an ion by the cation. So the factors affecting the polarizing ability are going to be the charge of the density of the cation. In this case, magnesium has more density charge than calcium does, and the size of the anion. So an anion will be polarized better if the cation is small and the anion is large. So as the negative ion gets bigger, it becomes easier to polarize. Thermal stability indicates how easy or how easily a compound will decompose on heating. And that is going to be affected by the polarization of the cation towards the anion. In this case, we are going to analyze the group 2 decomposition of the carbonates. So what is thermal stability? It means that a higher temperature is needed to decompose it. You can see here that beryllium is unstable at room temperature because the polarization forces the carbonate to split into carbon dioxide and the oxygen -2 ions, or the oxide ions. So the more polarization, the less stable will be, and that's why we can say that we need more energy to decompose barium carbonate than strontium, than calcium, than magnesium. Of course, beryllium carbonate is not included in this trend because the beryllium carbonate is unstable at room temperature because the polarization is very big. In general, the stability of the carbonate increases down the group. The thermal stabilities of the nitrates in group 2 are very similar to the carbonates. The bigger the size of the cation, the more stable they will be. In general, we have a metal with a nitrate. This is in group 2 only. So they are going to form the metal oxide, and they are going to decompose in nitrogen dioxide and oxygen. The example is magnesium nitrate, that is going to decompose in magnesium oxide and nitrogen dioxide and oxygen gas. Similar trends are observed here than in the carbonates, and the metal ions are larger as we move down the group. So all of them have the same charge. That means that the density charges decreases down the group because the cations are getting bigger. The bigger the charge density of the cations will polarize the nitrate ions, the same as happens with the carbonate, but to form, in this case, the oxide ions, nitrogen dioxide and oxygen gas. The more polarization, the less stable will be, and we are going to have more stability as we go down the group again. So barium nitrate is more stable than calcium nitrate, than magnesium nitrate, and again beryllium is not included in this trend. There are no numbers available to analyze the actual values for this, but there you need to know only the trend. Before talking about the enthalpy changes in solution, we need to define more or less what dissolving means. And when you put an ionic compound in water, the water molecules are going to surround it, and the negative side of the water molecule, that means the oxygen side, will be attracted to the positive ions in the lattice. And if the water molecules attraction overcome the lattice energy, or the lattice enthalpy, the positive ion will be extracted and then will be surrounded by molecules of water. The first process, the extraction, means the dissolving process. The second part, where the ion is surrounded by molecules of water, is called solvation. The same happens with the anions. The anions will be attracted by the positive side of the molecule, which is represented by the hydrogens in here. So if the positive side of the molecules of water, when they surround the ions, overcome the lattice energy, they are going to be extracting those ions, and then the process of solvation occurs as well. One of the definitions that you need to know for your Cambridge examination are the enthalpy change of solutions and the enthalpy change of hydration. The enthalpy change of solution is the energy absorbed or released when 1 mole of an ionic solid dissolves in enough water to form a very dilute solution. That means that the water is in excess and a lot of amount. So in this case, we have the magnesium chloride that is solid plus water, largest amount of water, and they are going to form magnesium ions in the aqueous state and the chloride ions in the aqueous states. In this case, the enthalpy change is negative because the process is exothermic. And if you analyze the same situation for the sodium chloride, you're going to see that the values of the enthalpy change of solutions are positive in this case. So AQ represents a large amount of water. It can be positive or negative. You can see here is negative and here is positive. So the positive should be endothermic and the negative is going to be exothermic. A compound is considered soluble for small values of delta H, and for large positive values, the substance is relative insoluble. So soluble and insoluble are relative terms because if we talk about, for example, lead carbonate, the lead carbonate dissolves in water, but the amount that is going to dissolve is so small that it's considered insoluble. The second term that, or definition that we need to know for our examination is the enthalpy change of hydration, and is that the energy released when 1 mole of gas ions are dissolved in sufficient water to form a very dilute solution. Be careful with this because in this case is energy released. That means that they are always exothermic, and this energy is responsible for providing the necessary energy to overcome the lattice energy. In other words, we're going to talk about this again when we cover entropy, but basically if the energy of hydration is enough to overcome the lattice energy, we are going to have a solution process. In this case, we have on the graph a Born-Haber cycle, or the Hess cycle, better said, in this case, for the solution of calcium chloride. And you can see that the calcium chloride is going to be separated into those ions. That is the lattice energy, but negative. Be careful with that. We define the lattice energy as the energy released when the ions in the gas state are forming the solid. But in this case, be careful because we are not talking about the lattice energy. We are talking about the opposite process. That's why it's positive. You can put the arrow in the other direction and change the sign. There is no problem with that. Also, when these ions are surrounded by water, we are going to have the enthalpy change of hydration, in this case of the calcium ions and the chloride ions. Again, be careful because we have 2 chloride ions, so we need to multiply that by 2. If we have the lattice energy and also the enthalpy change of hydrations, we can calculate the enthalpy change of solution for that substance using nothing else than Hess law. Characteristics of the enthalpy change of hydration. They are always exothermic. The value is going to increase with the density charge. And the more exothermic, of course, is going to be for smaller ions with the same charge. We already talked about that because that depends on the size and the charge are going to define the density charge. For example, lithium is more exothermic than sodium because lithium has more density charge. The more exothermic with similar size ions are going to be defined by the charge. So magnesium 2 plus is more exothermic than lithium plus because of the same reasons that we talked about in prior slides. In this graph, you can see the Hess law for calculating the enthalpy change of hydration. If you have the lattice enthalpy of the substance from the gas ions to the ionic solid, that means the energy that is released, this value is going to be negative. And you have the enthalpy change of solution of the ionic solid. If you add them up, you are going to be able to calculate the enthalpy change of hydration of the cation and the anion. Be careful with that because you have them separate. These ones most of the time includes two arrows, one for the anion, one for the cation, and if the anion or cation are in more than one amount, you need to multiply those values. Okay, in this case, we are going to calculate the enthalpy change of hydration of the chloride ion using the lithium chloride lattice enthalpy, the enthalpy change of solution of the lithium chloride, and the enthalpy change of hydration of the lithium ion. When we build up the cycle, the Hess cycle, we can use a Born-Haber cycle also, but with this one, it's much simpler maybe for you to understand. We can calculate the delta H of hydration of the chloride ion. On the right, you have the math. The lattice enthalpy doesn't change the sign. The enthalpy change of solution doesn't change the sign either. And the delta H of hydration of the lithium chloride, since the arrow is going in the opposite direction, we are going to change the sign for that. In this case, we can calculate that the enthalpy change of the hydration of the chloride ion is negative 364 kilojoules per mole. We are going to analyze the solubility of the group 2 sulfates. And the group 2 sulfates, the solubility decreases when, and you can see this one, it decreases when the size of the ion increases, and that is because the enthalpy change of hydration of the ions increases when you have a smaller ion. All of them have +2 charge because they are all in group 2. So the enthalpy change of hydration is going to increase when the size of the ion decreases, or you can say when the density charge increases. Now, sometimes you have problems remembering this, but remember that when you put magnesium with sulfuric acid, dilute sulfuric acid or concentrated sulfuric acid, it is going to form magnesium sulfate, in general a solution, and you do not see any precipitate. So you can remember that magnesium sulfate is soluble, and barium is used in the other hand to detect the presence of sulfate ions. So that is because barium sulfate is not soluble. If you think about that, you're going to see that the solubility decreases down the group, and you can see that the amount of barium sulfate that is dissolved in mole per decimeter cube is really, really small.